leading an effort for TTT entitled AlloyX. Tim, welcome to Imagine Aviation.
Thanks, Steve.
I'll turn it over to you for your presentation, and then I'll come back on a little bit later for some Q&A. Take it away. Tim, you may be muted.
Oh, yeah. Let's see here.
I'd be glad to describe your work for you, but that would entitle everyone tuning out in the entire conference. So I think it's valuable that you share your work because you've earned it. So go right ahead.
Now, everybody can see my slide. We're good. All right. Thanks.
All
Steve.
good.
Sorry about that. Yeah. So I'll be giving a small talk on some high temperature alloy development that has led to some breakthroughs into I think where the future of where high temperature metals are going. And I'd like to start with some background. This project really came about through a conversation I had with combustion engineers at our center, kind of across the center, where they wanted to 3D print new combustor dome designs, with nozzles. So really complex channels and cooling surfaces, and it's something that you can't produce with conventional machining. And so they reached out because they were having issues being able to print a component like this that could operate at extreme temperatures, 2,000 degrees Fahrenheit or higher. And they said, hey, is there a metal that we can use to print to make these components where it won't crack and fail almost immediately after testing? And we kind of sat down real quick, and the answer that we had was no. No, there isn't, actually. And maybe that's something that we should look into and see if we can't try to develop, a material that we could 3D print for these new combustor domes. And so, when we went and kind of looked at the drawing board, the issue being is that the temperatures they want to operate at, 2,000 degrees Fahrenheit, is a very extreme temperature, especially at atmosphere. And if you look at, the conventional metals used in aerospace, aluminum, titanium, and even your high temperature superalloys, they just don't have the properties to be able to withstand and survive those extreme temperatures. And so we're really limited about what type of materials we can use for this application. But if you kind of look at the graph here on the lower left, one class of alloys called oxide dispersion strengthened alloys actually provide a huge boost in your usable operating temperatures. So oxide dispersion strengthened alloys, or ODS alloys, were actually worked on a lot back in the 70s and 80s. And they showed really fantastic properties. The issue is, for an ODS alloy, what you want to do is incorporate nanoscale oxides into your metal alloy. The problem is doing so is really difficult. And you can imagine, oxides being much less dense than your metal. If you melt the metal, all of those oxides will just float to the top. And so, being able to cast apart with, these little oxides in your component is just impossible. And so they developed this really complex processing route where you basically mechanically alloy the oxides by just slamming it into the metal powder over and over, and then consolidating that powder into a part. And because of how complex that process is, ODS alloys really never became, economical, and it just, other than some special cases, just wasn't used within industry. And so a lot of the research and development of ODS alloys kind of fell away. But, since we're doing 3D printing, I wanted to, the question became, we're using a laser to build this component. Maybe there's a way we can incorporate these oxides during the 3D print process itself, and we can avoid all of that expensive and complex manufacturing that was needed for ODS alloys back in the 70s and 80s. And so that was kind of a fundamental question that led to this project. Right. So to start, we also needed to pick the type of alloy that we wanted to use for this project. And at the same time we were looking at different materials, there had been a lot of studies recently on a class of alloys called multi-principal element alloys, or MPEAs. Basically where you don't have one dominant element or metal taking over the alloy composition over another. And so one composition that was really of interest to us was nickel, cobalt, chrome. So equal amounts of nickel, cobalt, and chrome. A lot of studies show that you actually overcome this strength ductility trade-off. So you can keep your metal ductile while also attaining really high strengths. Another thing that was really exciting about nickel, cobalt, chrome is that it's stable from melting temperature all the way down to room temperature, where the microstructure isn't going to change a lot in terms of forming other phases in your alloy. And so you can basically thermally cycle to really high temperatures back to room temperature, and your overall composition microstructure is going to stay consistent, and your properties should stay consistent. And so that was really encouraging for us in terms of looking for an alloy that we can use for really extreme temperatures that you're going to thermally cycle. And lastly, this temperature difference between its solidus and liquidus temperature, the area where it fully melts or fully becomes solid, is a very narrow temperature range. And what we're finding is that if that range of temperatures is narrow, you can actually, it appears it's a more printable alloy for additive manufacturing. You're less likely to form segregation, cracking issues, and high residual stress. And so nickel, cobalt, chrome seemed like a really nice alloy to start with, but now we had to figure out how we're going to incorporate oxides into our process and into our printed part. We did start with mechanical alloying, just really briefly, and the issue, what we found was that when you mechanically alloy and you're trying to basically mechanically force those oxides into your metal powder, you destroyed the morphology of that powder. What was used to be very spherical and able to flow in your 3D printer to build parts is now deformed, much more platelet-like. It has a tendency to stick and becomes much more difficult to print. And so you keep incorporating other defects and issues into your powder when we tried to do that. And so we kind of quickly gave up on pursuing mechanical alloying as a route. And what we ended up doing instead was actually coat the nickel, cobalt, chrome powder with nanoscale yttria. Yttria is yttrium oxide, and it's usually the type of oxide that is used for ODS alloys. It's very stable and very inert, and it seems to actually help your oxidation properties when you incorporate into your metal. And so through a process called acoustic mixing, so it's a high energy mixing process, we found a way that we could coat our nickel, cobalt, chrome powder that we purchased for additive manufacturing, and coat it with the yttria, and then take that coated powder and put it into our AM machine. What was really nice is even after coating it, we didn't change the morphology of the powder, and the flowability of the powder was just as good, if not a little bit better. And so we were able to put it in the machine easily and start printing with it. And through some trial and error, we were able to find parameters that was able to take that coated yttria and break it up and fully disperse it randomly into our AM build. And so we had just basically nanoscale oxides throughout our microstructure. They're not agglomerated on grain boundaries or even throughout the metal part itself. So just nanoscale nickel, cobalt, chrome ODS components. And what you can see here on our graph, AM nickel, cobalt, chrome, that is nickel, cobalt, chrome without oxides. And then just by incorporating the oxides, you can see a improvement in your high temperature strength by doing so, basically forming an ODS alloy. And so we were incredibly excited about these initial results. And we also found they were more ductile and provided even better creep strength. All right, but nickel, cobalt, chrome wasn't really the composition that we wanted to stop with. And so after this initial success in proving to ourselves that we could produce ODS alloys with AM much more cheaply and efficiently than we could ever have imagined a few decades ago, we decided to take a model-first approach and to design a new composition based off that fundamental nickel cobalt chrome alloy, where we try to achieve 4 goals. One, we wanted to maximize our solid solution strengthening in the alloy. So basically add some larger atoms and smaller atoms into it, and just add some lattice strain that would provide strength at higher temperatures. We wanted to keep that printability, keep the solidus and liquidus temperatures that range narrow. We wanted to form actually carbides on the grain boundary. It's a common technique for high temperature alloys. If you can form carbides on your grain boundaries, it avoids grain boundary sliding and gives you a boost in your high temperature stability and strength. And then lastly, we wanted to be able to do all this without forming phases that would start to appear when we thermally cycle this component that would end up degrading our parts. And so this led to the formation or this new alloy that we're starting to call now NASA Alloy X810. And our initial tests, one, we were able to print it, and we were able to show the microstructure that was predicted by the model. And so that was right off the bat a really encouraging result, and helped support that some of these thermodynamic models are becoming robust enough to help us actually design new alloys moving forward. But then we started to actually test the high temperature properties of this new alloy X810. And if you can see here again on this graph, X810 is this yellow curve or yellow star. And you can see just with this first try at a new composition, comparing it to that initial alloy composition of nickel cobalt chrome without oxides, we've doubled the strength at 1100 degrees Celsius basically. But what you can't see from this graph is that not only is the strength double, but the ductility is almost 3.5 times better than the nickel cobalt chrome without oxide. And so you can imagine it takes now significantly more energy to actually break a component made out of this new alloy compared to the nickel cobalt chrome without oxides. And lastly, if we look at its pre-rupture life, so basically the life of the component under a static stress at this high temperature. We right here on the graph, we're seeing a 200x improvement compared to nickel cobalt chrome and other conventional superalloys. But the fact is that those tests were actually still running for X810 when we made this graph, and we're now getting to the point where we're seeing 1000x improvement in its pre-rupture life compared to nickel cobalt chrome. So you can imagine we're in temperatures and stresses now where conventional superalloys would almost instantly break, and we have now components that's lasting thousands of hours. And so we're really excited about where this new alloy can play a role in advancing aerospace technology, and and the fact that now we can use models to even help guide us in choosing where to take our alloying new alloy designs. And so I think that's kind of the gist. And I guess Steve, are there any questions about this work?
Yeah, we absolutely have some questions, and please, for those of you watching, load some more into the IL tool. We'll get to as many as we can. But as those are being loaded in, I had a quick question. You mentioned your process. Can it be used with any metallic powder or alloy systems, or is there specifics that you found more successful?
Yeah, no, that's actually a really important point. What's so great about this new approach to forming ODS alloys, and especially this coating technique, is that we can really take any nanoscale ceramic and any micron scale metal alloy and successfully coat it, and then be able to actually try to print it. We've already successfully coated titanium alloys, tungsten alloys, other refractories like niobium, C103, and we've already used a wide range of ceramics, hafnia, hafnium carbide, zirconia, and like you saw in this talk, yttria. And so this approach in itself has completely opened up a whole new alloying design space that we're just now starting to explore. And so it's actually a really exciting time to see, what other improvements we can make to other metallic systems.
Yeah, in your first slide, I saw the term refractory alloys. Why didn't you just pick refractory alloys?
Yeah, that's a common question I get a lot of times when I present this work. For two reasons, really. One, yes, they do have they much higher melting temperatures, but the application that we were really designing for is used in air. And refractory alloys have really terrible oxidation properties, to the point where at these extreme temperatures in 1 hour, the whole part could be completely crumbled into dust, like that bad of oxidation properties. And so you would have to have a whole other coating effort to try to realize a component like that. And secondly, too, we wanted to start in a system where we know that we can actually print this alloy easily. And so we wanted to avoid a lot of the cracking issues that would arise if we tried 3D printing refractory alloys.
Okay, that does help. There's a question in the IO tool. Do your measurements for these materials match your predictions? Do you even make predictions via molecular simulations? Or is this more of a trial and error type development?
So we didn't try to predict the mechanical properties itself. What we used our modeling tools was predict the printability and the microstructure of this new composition. And so basically we use the thermodynamic models to say, all right, if we dial up the amount of, let's say, tungsten into your composition, at what point do we expect to see other phases appear? Or at what point is that solidus and liquidus temperature range become too wide and we're expected to run into printability issues? A good, interesting case about this is, without those models, I thought, let's throw molybdenum, refractory alloy that's used a lot in high temperature alloys, into this new composition. But the models clearly showed us that if we put in molybdenum, we would form intermetallics of sigma and mu phases that we would not be able to heat treat away. And basically would have been a huge waste of time and effort if we had actually went that route without using the models first. And so it was more to help predict the printability and the microstructure, not necessarily the mechanical properties in this case.
Right. Yeah, that's a significant benefit for using that model-driven alloy design. Are there other benefits to that approach?
So this is a small effort where and we're also doing an alloy design. So when we go to purchase new powder, it takes a while. It's more expensive. And we're really going to get like 1 or 2 shots a year at trying new compositions. And so you can imagine that if we had went the molybdenum route and really just kept playing in that sandbox, trying to find a good composition of molybdenum, when the models showed us there really isn't a good amount of molybdenum, we would have wasted possibly years, or maybe never gotten to a point where we were having any success at all. And so again, that model saved us a lot of time, a lot of resources, and able to get to this point.
Nice. There's a question in the IO tool asking about some of your outreach, some of the outreach you're doing. So what universities are you working with? Have you seen increasing emphasis on materials? And we know 3D printing has really sparked a lot of interest, even in K through 12 students. So have you done any outreach, or what outreach do you plan on doing, or could we do in this area?
So yeah, there's a lot of collaborations with AM. We have NRAs with a few universities, University of Pittsburgh and Arizona. And I will say, in terms of the ODS AM, this is still a fairly new project, but we're in discussions with other universities like UC Davis and even MIT about ways that maybe we can coordinate and help collaborate in the future. And so this is still I would say early on in this project's life, and we're really looking now at the point of we see something really promising. Let's see who can help out and see where we can take this.
Right. And there's another question in the IO tool that, again, maybe the answer will be we're early in this process, but Have you done any, or do you plan on doing any combustion tests with the new materials?
Right. We are in the process. I have a meeting next week with the combustion group here at Glenn to work on the actual design that we want to use for these tests. I will say, I didn't even really point it out in the second slide. We have printed successfully, dispersion strengthened combustor domes. So that's actually a 3D printed dome with the nickel cobalt chrome ODS using the design that was shown in the first slide. And so we've already been able to print, very complex designs with dispersion strengthened alloys at this point.
Nice, nice. You listed, I believe, in one of your charts or in your talk that you've had a 200 times improvement from the initial test. Do we think that's the ceiling, or do you think there's more to go?
Right. Yeah. No. Like I said, that test was still ongoing when we made the poster, and the number just keeps going up. This new alloy XA10 seems to be significantly more stable and compared to conventional super alloys. Like I said, if we compare it to nickel cobalt chrome, it's now to the point where it's over 1,000 times better. And so, yeah, that's a number you don't usually see too much when we're working on material science. So,
right.
Huge, really surprising. To be honest, when we first started to get these results, we thought something had went wrong with the test. But now we have a lot more tests now confirming that this is actually the case, and so we're pretty excited.
That's great. Well, then I'll throw an unfair question at you. When you incorporate the oxides, what are the limits to this process? Do you know the limits, or haven't you even? We'll get there when we discover them. We'll try and blow through them.
Yeah. No. Yeah. There is still a lot of work, even on optimizing, the amount of oxides we should coat the powder with. We've really been sticking with 1 weight % coating. It's a nice even number, and it seems to be giving us, good results. But we still, is something that we need a knob to turn. How much of these oxides can we incorporate into our component, and then is there a point at it's too much moving forward. And then also we've concentrated a lot at 1100 degrees Celsius. We want to now explore 1200 C, 1300 C, just kind of get a sense of how high of a temperature can we maybe take this new alloy moving forward.
There's one component of your research that when we spoke before, I found hilarious and beautiful, and it really chimes in with the rest of what we've been hearing about perseverance, about reaching levels of discomfort this whole time, about don't accept those challenges, learn from them. But tell us the funny story that would this technology have been developed the same way if we weren't in a pandemic?
It wouldn't have. It's actually a really good point. We had just started doing the nickel cobalt chrome ODS, and I think I had probably already come up with a new composition that I think we would look at. Again, had a lot of molybdenum in it, but then the pandemic happens. Everyone got sent home. Things slowed down, and we were kind of forced to figure out what we could do at our kitchen table for a while, and that's really where it gave us time to look at these modeling tools. I'm an experimentalist at heart, and so that's not usually my first go-to. But we had the time, and we had the tools available. Let's sit down and see what the models can guide us. We had the time. Let's do that and see what answer we get. And at this point, I'm happy that we had that chance, because I don't think I would be presenting the results that I am at the moment without it. So I guess the small silver lining in all of this.
Right. Hey, we look for them all over the last couple of years, but
right.
That is just a wonderful part of the story. Dedication to your perseverance of you and your team. There's one more question in the IO tool I want to get at. It's a little more technical than my romance story about how we work in the pandemic. But how much weight reduction can this new alloy provide?
Yeah. So we're looking at. There's actually two things. You actually do reduce the density of the metal composition itself by forming oxides. Oxides are less dense, And so you actually can make it slightly lighter just by the fact of forming the oxide, still not too much. But you can imagine, having an alloy that can operate at higher stresses or higher temperatures means that maybe you can just make a component that's just not as thick. And so you can actually just lighten your component as well. And so that's another advantage you can take by using a material with these better properties. And so that how much you can actually take off, that'll have to go to the structural engineers, but theoretically you should be able to lighten your components moving forward with these new alloys.
Oh, that's excellent. Tim, last question. What excites you about your work and the potential that this work can provide in effect going forward in civil aviation?
I think it's rare to have, I think, a material where you can see huge jumps in properties like this, and so I feel like it really it kind of opens up the design space a little bit in terms of what components you can make. And for example, a 3D printed combustor dome. 10 years ago, I don't think that's something that we really would have taken much thought of as being a possibility. But now we can create these incredibly complex channels and flow streams with even better metals than we could do conventionally. And so how that improves and changes aerospace, I think, is going to be a really exciting thing to see in the next few years and decades.
Oh, that is great. So, Tim, I really want to thank you for your presentation, for answering all these questions, and for your work on TTT and the AlloyX. Thank you very much, Tim, for joining us at Imagine Aviation.
Thank you.
Great. I hope we're going to shift to a break, but I hope everyone really enjoyed all those TTT presentations. It is that infuse that we're talking about on day 3. It's how we take this to the next step, and it's very, very exciting, and so glad to hear. So we are going to take a quick break here, but before we head to break, I did want to remind everyone that at conclusion of today's session, we will again be heading into GatherTown. Now, GatherTown is a great virtual space designed to mimic the experience we'd all have in an in-person conference. It's been a great success over the past 2 days, and we encourage you all to join. Inside of GatherTown, you have the opportunity to see USRC poster sessions, meeting and talking to the students about their work and what inspires, invigorates them. There's STEM rooms with activities for all, including a game room, Dream With Us activities, and abundance of knowledge, and social networking. Social networking is what we all really miss from these conferences, and we're going to envision that. We're going to have that. In fact, I heard there's a rumor that there'll be a virtual happy hour in the virtual rooftop lounge at 5 p.m. Eastern today. So please feel free to bring your own choice of beverage and join us to celebrate the success of this Imagine Aviation Conference. So I'd like to step aside for a brief time, and we're going to come back with an excellent panel discussion regarding the runway to a new sustainable society. It's going to be something you do not want to miss. Thanks for joining us today at Imagine Aviation, and we will be back at 10 past the hour. Thank you.